Tom will talk about how he has come up with a model to handle partition imbalances in Kafka Cluster.
Thanks, Nathan, for the beautiful introduction. Hello, everyone. I work for the Siphon Database team in Microsoft. And Siphon is it's built with Kafka as the backbone, and it's a distributed message queue system for any team to internal team in Microsoft to onboard and do stream processing.
Try the other people.
All right. So we process about 4 million messages per second. That's just the average ingress. We peak up to 6 million messages per second sometimes. That amounts to almost 800 terabyte just ingestion per day. That's not taking into account how much gets dequeued from the topics. As you know, a topic can be dequeued multiple times. So if you add that all up, we go into like 4 terabytes per day. We have really big deployment clusters for Kafka. We have 1,700 Kafka brokers as of today. That's across a few clusters. That's not a single cluster, but the biggest single cluster that we have today is something like 350 brokers. Our key customers among the internet teams in Microsoft are from Bing Ads monetization team and Office 365 teams and many analytics teams. You can see our growth has gone up exponentially this year. That's a little bit of high-level architecture diagram for Siphon. It's mostly built out of open source components. You can say Kafka and Zookeeper. And what Siphon provides is a collector system for ingestion and consumer API on the other end. We have also built an audit trail system so that we can account for each message that goes through this system, even at this high message per second throughput. From the consumer end, Kafka provides a pull API by default, but we have also developed a push API model so that our customers can come and say like, hey, we want this topic A to go into Elasticsearch, or we want it in some other database. And it's just a matter of configuration to check in, and the data starts flowing in seconds. All right, so my focus of today is, well, how many of you are engaged in actually managing Kafka clusters in daily operations? A few people, all right. So I do the same, and it can be a nightmare really because of the skewness in how the partitions are laid out across a huge cluster. When we started with like a proof of concept with like 5 machines. I could, at top of my head, we had these 5 or 10 topics and the customer names really. But as we grew into 1,700 Kafka brokers and hundreds of topics, there's no real way or any GUI. Nothing can help you in getting a picture of what's going on. So I try to create something that will drive it on autopilot more and relieve me of some stress there. All right, let's take this example. We have 3 machines in our cluster, and each machine has 2 disks, and the red color shows how much of the disk is utilized. By utilization, I don't mean how much space utilization. It's more of first the bandwidth utilization, the MBPS that the disk can take. In this example, you can see the machine number 1. The first disk is almost fully utilized. Disk number 2 is not. And you would wish, hey, can I move some partitions from this 1 to this 2? That's what you would wish, and you have to do it manually. in machine number 2, disk number 2 is completely cold, and worst case, machine number 3 is completely cold in my cluster. And why this could happen is Kafka does a good job with laying out the partitions across the disk in a fair way. Let's say machine number 1 has to host 8 partitions. Kafka will do a good job with putting 4 partitions on disk 1, 4 on disk 2, but they can be, these things can be from different heterogeneous topics. And it could be just that the partitions on disk 1 is more I/O intensive than those things on disk 2. Why is disk 2 so cold in machine 2? It's just a new disk that we added to that machine, so the partitions won't just move there. It's not a common scenario, but it can happen sometimes when you decide like, hey, I've been utilizing only one disk. You go into JBoard configuration and you add the second disk to your Kafka configuration. And let's say machine 3 is a new machine that was added to the cluster. And then you have got some ops work to move these partitions into that. Okay, let's take a closer look at each of these problems. I like to observe this situation as a two-fold scenario. One, there is an imbalance of load inside a machine among the disks, and the other is an imbalance across machines in the cluster. Let's take the first problem where there is an imbalance among the disks of a single machine. So here you can see topic. The notation I've used here is like topic 1, partition 1, topic 1, partition 2. So the red color shows like topic 1 is a bit of I/O intensive topic. Kafka might think that it has laid out the partitions fairly well, 50% on top disk, 50% on disk 2. I assume disk 3 was added later here. Okay, how do we deal with rearranging this a bit automatically? So turns out a little hack can do it. It's not a very clean solution, that's why I call it a hack. I wish Kafka can put a clean solution someday. What I do is I just take all the topic partition names, sort them alphabetically, and then take the list of disks, sort them alphabetically, and then arrange the topic partitions in a round robin fashion across the disk. What that will yield is, you can see topic 1 partition 1 and topic 1 partition 2 will get into different disks, and then in alphabetical order we go 1, 2, 3, 4 and then 5. What this ensures is, if topic 1 is an I/O intensive topic, 2 partitions won't fall into the same disk. They are bound to go to a new disk. And also all the disks get their fair share of partitions. Does that make sense? Okay. So that was a simple hacky situation to get around that problem. Now let's take a closer look at imbalance across machines. So I'm switching to a new problem. So we have imbalance across machines now. So let's take this example where we have 2 brokers, 2 topics, each of them having 2 partitions. This is probably the most beautiful situation that an ops guy can ever want. This is fairly nicely well-balanced load. Now, broker 2 goes down. You have a requirement to create topic 3. You create it, this is how you get it. So now you can't do anything about it. Like you can wait for broker 2 to come back up. Maybe the machine is down for good for a good day. So machine broker 2 comes back up. This topic 3, partition 2, you wish would move into there, but it won't. On top of that, let's say you added a broker 3, partition still won't move in there. So what can we do here? All right, one of the approaches is a static approach, which Kafka's reassignment tool adopts. I feel like it makes some wrong assumptions about the real world scenario. It assumes that all the topics are heterogeneous, they are not all same. So the throughput requirement of partitions of different topics won't ever be the same. And the number of partitions of a topic cannot be just determined from the throughput requirement. There might be business requirements of partitioning the topic into n ways. And all the machines in the clusters are not of same configuration all the time. If you have a small cluster, you might it might just work out for you. But when we go 350, 400 machines, sometimes 50% of my machines have 3 hard disks, sometimes they have 4 hard disks. You never know. So what do I do in such a heterogeneous world? So let's take a look. Let's say I have these 2 brokers. You can see the partitions all laid out in a nice, fair way. It looks like that, but it might not be really fair, because what if topic 3, partition 1 here, is a high I/O intense topic? Maybe I would like to have it that way. And I would also like to have it in the other way if broker 1 is a lower configuration, lower hardware configuration broker. So a seemingly fair distribution is not necessarily practically fair in real world. So I thought, let me try out a dynamic approach. And this is what I call adoption marketplace. I have done a proof of concept implementing this idea, worked out fairly well for me. So this is how it goes. The program runs on each broker. Every broker decides for itself whether I should give out any partition for adoption out. If it decides so, it would do it using a Zookeeper adoption ad listing. The ad would look something like in the orange box there. Hey, I want to give out this topic 1, partition 1. And the requirement is that it's probably like 2 Mbps at peak. That's the advertisement broker 1 puts out. The other brokers, broker 2 and broker 3, observe the ad. If they both can take in 2 Mbps at peak, like if they have the extra bandwidth, they will try to lock on it. Whoever gets a lock on that ad would adopt it. I'll explain more in the following slides, but this is the general basic idea. So of course the logic, that tool runs independently on each broker, and it needs coordination, so it's a Zookeeper bag implementation. And a quick look on how the advertisement itself looks like. It looks like something like this. Of course, we need a version number because of future modifications. The item is named as what topic, what partition one wants to give out for adoption, and the resources required. Example can be something like this. As I said, we are trying to give out topic 1, partition 1, and the resources required is peak Mbps value 2. And the interface for the program is fairly simple, not too many methods out there. The bottom 2 interface, which is actually advertising out using Zookeeper and initiating the adoption process, it's already coded into the proof of concept code. I have open sourced it too. The top 2 portions, I have left it blank. I want developers to develop it on their own. The top 2 are basically how to find out what partitions you want to give out for adoption, and the other one, out of the advertisement listings, how do you decide which adoptions to adopt. I left it as unimplemented because that's where most of the contention happens in ideas. Like, hey, let's take the peak Mbps as our criteria to decide. Hey, let's take RAM. Hey, let's take CPU. Everyone has a different cluster, different machine requirements. So that's why I thought like, hey, let me take it open, leave it open, and let's see what all ideas people come up for it. The tool on each broker runs on a simple loop like this. First, it tries to find any local partition to give away for adoption. Second, if it does find something like that locally, it posts the ad and waits for somebody to adopt it. Next, it tries to find it tries to look into Zookeeper for any ads that other brokers might have posted, and then tries to lock on that ad and initiate the adoption process. The adoption process is nothing but the Kafka reassignment run of the reassignment tool for just that partition between two brokers. All right. Now, when I set forward to really implement this for my proof of concept, I implemented a very straightforward logic for this. Instead of really looking at the bandwidth or anything, I wanted a quick implementation, so I went for, I let the brokers see that for each topic, how many partitions are there in the cluster and how many brokers are there in the cluster, including the dead brokers. Now, if a broker is hosting more partitions than the average it should, it tries to give that out for adoption. For example, if there are 5 brokers in the cluster and there's a topic with 5 partitions, and the broker sees that, hey, I should be hosting just 1 partition, and I'm hosting, say, 2, it tries to give out 1 partition for adoption. So it will put an ad in the Zookeeper. And some other broker for sure has 1 less partition for that topic, and that broker would try to grab that partition for adoption. This is an example run that I did. I took a small cluster of 3 brokers. I brought down 2 brokers so that I have really 1 live broker. I created a topic, 10 partitions. You can see all the replicas, just a live broker there. Really not a good scenario to be in for a long run. But fortunately, I had my tool running, and over a period of time, all the partitions slowly moved into the live brokers as they booted up. So that's it. And the benefits that we get from a program is the Kafka reassignment command basically automatically runs in the background forever. And when you add new machines to the cluster, you don't have the ops overhead anymore. The older partitions will just flow into the new machines. And you can monitor the advertisements that are in Zookeeper. If you see like, hey, the advertisements are just lying around in Zookeeper, brokers are giving out advertisements but nobody is adopting them, it's time to add new machines. And of course, the logic to determine which partitions to give out for adoption or when to take in adoption is something that can be improved often, or actually developers should develop their own based on what they think is the best fit. And I have open sourced the code, a proof of concept on that link. Okay, thank you. Any questions?
This back here.
These are not yet, but they will be, I guess.
Yeah, we'll post this, yes.
I deployed it like probably 6 months back. It has its bugs, because that's why I call it a proof of concept right now. But it did a fair job of. We really had like topics with 300 plus partitions across the 350 machines, a bunch of them. And we used to have daily on-call issues where disk throughput would really jump off. But after deploying this, we had really less on-calls and something to mind, because it made sure that the partitions are fairly distributed in the cluster. Yes. Yeah. No, it can be 250 MB. What was the 800 terabyte? How much?
800 bytes per day.
So it's not per second, it's per day. I don't know if. Yeah.